Hi, it's Terry Dennery of the MathWorks. So in this video, well, the video is called Reduce the Mechanical Model and Make It Run Really Fast, right? And um, so in the previous video, we just kind of had this really good out of the box experience. We got essentially the differential equations and a program solution in .m MATLAB form. And the basic idea of this is that it solved for the second order differential equation for each of our revolute joints, and there are three of them. Okay. And we'll talk a little bit about what the fourth one is, but we'll get to that in a moment. All right. And what we're going to do is really reduce this, and we're going to match, you can kind of see it right here, that there is truly 1 degree of freedom, and that's the rotation of the motor. Okay. And it's because of that we can reduce it really to just 1 degree of freedom. So anyways, with that being said, let's just get this whole thing started. All right. And so this is my SimWise model, and we're going to go to Get Geometry, and let's run our Get Geometry app and import it to Simulink. Notice the directory initially, all it has is the SimWise file, terry4bar.wm3. My workspace is empty. The Get Geometry, let's kind of move this out of the way, because what you're going to see is, do you see that? Just added a whole bunch of files into my directory, right? And that, the one that I'm really interested in is this one, terry4bar_fd.text. So in the previous video, we kind of used this, and we got essentially generating a solution in MATLAB very quickly. All right, what we want to do now, though, is kind of address this issue with 3 degrees of freedom being reduced to 1. All right, and I'll even explain where the fourth one is and why it wasn't really represented with its own differential equation. Now, the differential equations, we're on the motor angle, which is given that variable name, and then these 2 revolute joints there and there, right? And the whole idea of why 4 joints can be reduced to 1 degree of freedom is that there is a mechanical loop connection, and that we see that in our mechanical model, that this goes there to there, and then the ground connection takes it back, and that's why it's called a 4-bar linkage. All right, and so that's called well, certainly that is a mechanical loop, but what we're seeing here is the constraint that imposes on the formulation, right? And so anyways, and we're going to do some really interesting stuff to really optimize the assessment of the loop. But before we do that, let's really kind of get into just the real, well, I'll call it mechanical, but I mean it in kind of 2 ways right now. That how do we really tell the tool, what we're going to choose to be our variables? And it turns out that the name that was chosen by my buddy Paul Mittagey and Professor Kane, kind of indicates kind of where the method came from. You'll see it's called set generalized speed, right? And if you're familiar with Lagrange's, approach, he introduced what they call, generalized coordinates, right? And I'd say that, there are lots of really important things Kane came up with, but one of the real keys was him recognizing that I don't need to operate all the way down to coordinate. Okay, and what I mean by that is if it's a revolute joint, the coordinate is an angle. If it's something that extends, the coordinate is a distance, right? And what he realized is that the equations can be assessed, or they can be formulated in terms of the speeds for each of those degrees of freedom, and that certainly introduces terrific efficiency in, I'd say, expression of the dynamic system, all right? But anyways, let's kind of proceed with this first, right? And so this is the one we want. We want the motor angle. And so the next 2, we're going to comment out. So the percentage sign is what comments that out, right? And so with regard to the constraint, and again, bringing the image of the model back, I am going to talk about how it's expressed. And essentially, if you take this vector length, add it with this vector length, this one, and then back here, that should be equal to 0. And that's exactly what's done here. And so they introduce this notation, which is pretty clever, I think, of throwing an angle bracket at the end of the variable name to indicate that this is a 3-dimensional vector. right? And so then with regard to it, kind of moving in this two-dimensional plane, um, that that you get two equations by essentially dotting it with an x and a y axis, right? And so what is sort of the out-of-the-box solution is referred to as an augmented solution. It means that you take the general equations of motion, the kinematics of each, revolute joint that's being accounted for, and then you add the two additional uh, algebraic equations you get from dotting with x and y. And so with those 5 equations, you can impose that loop constraint, and you have to solve for 2 additional variables, right? And these 2 are kind of good ones to have, because they're essentially the force required of the bearing to essentially hold the I'll call it the mechanism together at that one joint, which we represented with a spherical joint on a slot. Okay, so anyways, to be efficient in this demo, well, first couple things, right? So the change in notation is going from augmented to what they called embedded formulation, and you use this real interesting command called the solve set input dt, right? And it advises you, we'll comment out the next 2 lines because we're not solving for those variables anymore. All right, so let's do this and do this, all right? And now let's go get solve set input dt. So I practiced this ahead of time and got to work really well. And so I'm going to just go in and essentially copy the statements that will allow us to do this simplification. So let's go back in here now. Give ourselves a little bit of space. And I'll paste that in like that. All right, and so what it's going to essentially do is eliminate the 2 variables, constraint 14 and constraint 17, by including the equations that are formed by these 2 dot products, right? And so it means that instead of solving for all 5 of these things, we're going to reduce it to 1 equation, and we're going to just solve for that. And we're going to do things a little bit different this time, that this is not going to be a MATLAB solution, but this is intended to be a Simulink solution. And we'll see probably in the next video, we'll use a MATLAB function block to essentially, import what we're going to be creating here, right? And so we'll go ahead and instead of generating our file with the ODE command, it's this one right here. Actually, I think this is the way I'll do this. Control C, Control V, because I want that file name, right? And so here's essentially the operation, right? And this is simply about solving the algebra to get what we need. And let's put that in like that. All right, and I'll do one more thing. Okay, so I'm going to take all that and paste it, and we'll do our inverse mechanics too. So I'm going to inv will be the .m file's name, and instead of solving for this, we're going to solve for this, right? And it's going to give me a little bit of static about solving for something that I'd already set for 0, and so I think it works pretty well, but we'll find out. So let's go ahead and paste that in like that. Okay, and so now I'm ready to bring up MotionGenesis, so let's just launch that. Keep it in the window as much as we can. I think there, let's do it like that. Okay, and I think the way I'll do this is I want you to see the effect of solve set input dt. Hopefully I didn't miss anything. All right, and so we'll run the first 88 lines first. So copy, and we'll paste that in. It's really cool just to kind of go and watch how a symbolic tool will work, but it's essentially taking all that input and driving these equations for us. And so I'm going to run that, the solve set input dt. Okay, so it's looking like it's working pretty well. All right. And at this point, this is merely an expression, I'd say, mostly of the kinematics. Um, Actually, it's completely all kinematics at this point, right? And so now we go in and apply the forces. The only forces really, well, torques are well, they might be in that formulation. I'm not sure. Actually, we'll find out. So they certainly get there by the end, right? And so what I'm going to do is add the forces of gravity, and then let's solve for the equations of the overall system, right? And again, what I'm telling you is that the approach we're taking this time is to reduce the system to 1 degree of freedom, right? And here's where we do the system dynamics, and I hit enter. And so that's beautiful to me, all right, because I can see it already at line 230. Yeah, that Keynes equations, which is a system of equations, is really a single system. Or I'd say a single equation represents the system of equations. And ultimately, the approach, if you just for your information, is that what's inside those brackets should be equal to 0, right? And so now we're going to just kind of wrap up on the solution. And so I want you to, again, notice what's in my directory. We'll code the forward dynamics first. I'll paste that, and MG4 bar was created, and we'll just do a quick look on it. And that makes me really happy. There's only one second order derivative variable now, and that's the motor, by the way, too, right? And so this last piece is a little bit more of a make sure I cross my T's and dot my I's kind of situation. All right, you'll see what I mean as we get this. All right, and it has a lot to do with kind of having to initialize some of the variables. So let's copy that. And this time we'll see one that should be called inverse MG Terry 4 bar if I do everything right. Okay, so torque motor GA, all right? That I did set that to 0. And yes, I do want to overwrite it. And it's going to even ask me, I think, a couple more things. Right, to generate code, press enter to continue. Input a value for, and we'll see this in the next video that I'll probably be in a position to better explain why it wants to set that to 0. But all right, looks like it worked. And there's inverse mechanics, or inverse MG Terry 4 bar. And I love that. Okay, so it's solved for that torque, assuming that you provide the position, velocity, and acceleration of the trajectory that you want for that motor. So anyways, thank you.